Hello folks. In today's video, we're going to take a look at a collection of special effects and functions in Sample Wrench, including how you can generate waveforms, how to differentiate and integrate them. Yes, a little bit of calculus on your waves, always fun. We're going to look at reversing, inverting, rectifying, a transfer function, a sort of retro grunge function, and then the reverse of that, which is a click and pop removal tool for recordings of vinyl albums. So the first thing we're going to look at is how to generate a waveform. And I'm going to pop open a new editor over here, and we're going to go down to the generate menu item. And we have a series of things we can generate. Simple sine wave, a true square, and true triangle. And by true, we mean they're appropriately bandwidth limited. Simple sawtooth, variable pulse, a noise, or blank, right? Just silence. We can set up the sample rate, the frequency of the waveform. There's other frequencies we can actually set in here if we want to make a more complicated waveform. Sine wave partials, think of those as. And of course, our usual series of presets. So what I'm going to do is I'm going to start by making a little square wave, a true square wave. We'll use the standard 44.1 kilohertz. I'm going to change the frequency. I'm going to bring this down to about 150 hertz, just so it's not screaming in our ears. And we don't need 10 seconds. 1 second will be good enough. Okay. Boom. So here's our square wave. Now you might say, hey, what's with this variation over here? So I'm going to zoom in a little bit. And what you can see, and if we move around here, it'll change a little bit. You can see these little sort of spikes, little horns. This is appropriate for a bandwidth limited square wave. Right? So this is limited to the audio band. This is limited up to about 20 kilohertz. It's really only when you extend the frequency out to infinity that these corners become perfect 90-degree angles, and this is exactly square. All right. If you don't do that, and if you really want that kind of square wave, you can generate that with the pulse function. That actually produces some alias frequencies. You might like that, but in any case, this is our waveform. Right? Just give this a listen. Just a simple pulse, right? Simple square wave pulse. All right, now what can we do with this? Well, let's do something a little bit different. I'm going to come over here into the effects, and I'm going to look at integration, right? Integrate the waveform. If you're familiar with this function from calculus class, this is going to give you the area under the curve. Now, because the square wave is constantly changing, right? It's going up and down, up and down. What we see in the positive section is a positive ramp as the area increases. And then when it goes negative, we see that ramp decrease. So we basically get, or should get, a triangle wave out of this. All right, so let's integrate this waveform. Oh, what the heck is this? I can't see this. This is just crazy. Let's zoom in a little bit. And now it looks like we just have these little pulses, right? And it's like square, like what the hell is this? Well, in fact, what's happened in this waveform is that the integration has produced a wave that's bigger than 100%. Now, because Sample Wrench uses a 32-bit floating point internal representation of the wave, this is not clipped. This wave actually does exist, like way out here, a couple stories high. And you can rescale this thing to get it back into the normal, 16-bit sort of range that you would see on a CD. And all you have to do that is come down to your level control and then just say maximize, scale to full. And it understands you want 100% of, the ordinary 100%. And boom, here's our waveform. And if we zoom into it, you will see, in fact, yes, this is a triangle wave. Right? There's a little DC offset on it because of, we started with a positive pulse, a full positive pulse. So, if we go all the way back to the beginning here, you can see that's the area is coming up, and then it goes negative, and the area goes down, and so on and so forth. Right? So we have a triangle wave with a little bit of a DC offset. If you wanted to get rid of that, of course you could. But what's the inverse of integration? Well, that's differentiation. Take a derivative. What's the rate of change of this thing? So if we differentiate it, we should get our square wave back. Hey, it's really tiny. Yeah, because remember what we did, right? We scaled it down. If we zoom in on this, you will see that, in fact, you have a square wave. But we can, of course, go back to our level control, do a maximize, scale to full, boom. And unlike an integer representation of the waveform, you're not really going to lose anything when you have a really tiny wave and you maximize it out, because this is a floating point representation. All right, so beautiful. Integrate, differentiate. You can do this with complex waveforms. Just something to remember. Integration basically is kind of like a low-pass filter. It produces a 6 decibel per octave decreasing slope. And differentiation is the exact opposite. It produces a 6 decibel per octave increasing slope as we go up frequency. So, you can use these things to sort of change the sonic character of a sound. All right, cool. Okay, let's move along to something a little bit different. Let's just, we'll just get rid of him. We don't really need that waveform anymore. And I've already loaded a couple of waveforms over here. So this is our favorite fire sign. What about the job displacement market in this city of the future? That we've used a million times. So what we can do, a couple of simple things, right? We can go in and do a reverse. Right? So this is backwards, and if we play it, right, so that's, hey, backmasking. And if you, in fact, use the scrub tool, you might remember the scrub tool, you can use this to listen to the sound, right, just by rubbing this over the surface. Right, you see that's backwards. But remember, if we use it in the backwards direction, so I'm going to click here, hold the button down, and go back in the city of the future. Right, so I'm playing it backwards, so I can hear that. All right, let's bring this back. Another thing that we can do is to invert the wave. So this basically flips the wave top to bottom. So the reverse, right, the front becomes the back and the back becomes the front. When we invert it, the positive becomes the negative and the negative becomes the positive. So we're like rotating it around the horizontal axis. Now, that is not going to sound any different by itself. What about the job displacement market in this city of the future? This is useful when you need to get phase, absolute phase, correct on multiple waveforms. It also has certain analytical uses, one of which I will show you down the road. Okay, other things that we can do. Well, how about rectification? Full wave and half wave rectification will generally produce distortion. Depending on the source, it can be extreme or it can be a little bit more subtle. Basically, it's going to take the negative portion of the waveform and either flatten it out, make it disappear, which is half wave, or flip it so it becomes positive. That's what full wave is. Right? So that's all gone. Let's play it. What about the job displacement market in this city of the future? Right? So in the voice, you get this kind of fuzzy effect, right? A distortion effect, which might work well on an instrument. That might be an effect that you want on voice, but more typically people would be looking at instruments for that. And here's the full wave version. What about the job displacement market in the city of the future? Okay. Now, let's get beyond that. Let's go to the next crazy level. And that would be transfer function. So a transfer function does, this is a little graph. The horizontal is the input and the vertical is the output. So you draw with the little pen over here a shape that warps the input onto the output. So this straight line means, well, hey, whatever the input is, that's what you get for the output. This is basically like an amplifier with a gain of 1. It's the same. This doesn't change anything. And we can see some of the different presets that we have over here, right? So here's an inversion. So here the input is negative, but the output is positive. Over here, the input's positive, the output's negative. So this is essentially the inversion thing that we looked at just a moment ago. But we can do lots of other weird stuff, right? So we can do like a hard gain. So this gives us like a gain of 10, and then when we get signals above that, it just clips it, right? So this is, you know, basic like guitar fuzz kind of a thing. You can see how much this is cranked up.
What about the job displacement market in the city of the future?
Right, so obviously cranked up there in terms of volume. We can look at some other sort of crazy kinds of things here that we can do. And take a look at like a logarithmic kind of curve, or
what about the job displacement market in the city of the future? What about the job?
Right, so you can definitely hear some fuzz on there. It's not quite like the preceding one. When you get these weird kinds of things, you can get some really weird sorts of subharmonics and so forth created.
What about the job displacement market?
And like I said, you can just draw something weird. If you go backwards, it'll erase. All right, so I'll just erase that. I have no idea what this is going to sound like.
What about the job displacement market in the city of the future?
Just a different kind of distortion, really. All right, so you can play around with this and have some fun. But it has good analytical purposes as well. There are things you can do with it that are sort of fun. Anyway, back to our original.
What about the job displacement market in the city of the future?
Now, some people like to use sort of a grunge function, a retro function. So we have something to do with that, our grunge function, and there's different things you can do. You can just do a bit depth reduction, so it makes it a little bit more coarse, a little more granular. You can add hiss to it, and you can add clicks and pops, like on a vinyl album. So what I'm going to do is the usual presets, of course. What I'm going to do is sort of modify what I have right here. I'm going to leave the 8-bit, right? And then I'm going to add some clicks and pops. So what I'm going to do is I'm going to take the density of these clicks and pops, and I'm going to bring that up to about 90-ish%, somewhere around there. And then the level, how loud they are, right? Bring that up to maybe 60-ish%. Okay, so all these little things, these little spikes that you see, these are all the little clicks and pops.
What about the job displacement market in the city of the future? What about the job displacement market in the city of the future?
All right, so you can hear that sort of little rumbly background thing from the 8-bit reduction. And then obviously we have all those little clicks and pops. So you can run that multiple times. There's different things you can do to it to really make something sound old. You know, there's, like I said, a hiss on there, so that if you want to mimic like tape kinds of noise, you can do that too. But most people probably are thinking in terms of, well, I would like to get rid of that stuff, right? I don't want to keep it. I don't want to make it. I mean, sometimes you have a need for that, but I want to get rid of it. All right, so here is a recording. This is, as you can see, it's got a lot of little spikes in here. This is a digitized vinyl album. It's actually the title track of Emerson, Lake and Palmer's Trilogy album, an album I picked up many, many years ago when I was in high school. And that vinyl album had been played and played and played and played, and there are lots of little crispy crunchies all over the thing. So this is just a little outtake, a little bit less than a minute, and you'll be able to hear all of that sort of analog vinyl badness. Okay, clearly not sonically pristine. How do you get rid of these things? Well, you could, if you just have a couple of them, you could just zoom in. I'm just going to grab this big one right here. Just zoom in on this. There's the spike. And you could get your little pencil tool and draw this out. And even though the wave you come up with won't be perfect, like I can just estimate and say, oh, it's going to look something like that. Even though it's not perfect, it's going to be way better than that click thing you had a moment ago. All right. However, look at all the things you have here. And there's a whole bunch of these that you can't even really see. You can hear them, but they're like down in here. So trying to scan through this would just be a royal mess. And what we have to help with this is a click and pop removal tool. And it's pretty simple to use. Right? You just indicate which level you want. If it's pretty bad, you can just grab the aggressive. If you want to be very careful about it, right, use the conservative. Normal is, typical. I'll just use the normal on here. Hey, look, virtually everything's gone, right? Here's a couple of clicks that are still left. And just to show you, right, I'll come in and we'll use the aggressive this time. Right? So remember, we did have a couple of spikes out here. And aggressive took them out. All right, so what did that do to the audio? Did that really mess with the audio?
To mend the love that ended long ago, although we still pretend our love is surely coming to an end. Don't waste the time, you've got to love again.
All right, that's pretty nice. You don't hear a lot of artifacting going on there. Okay, a noticeable difference. All right, now I'm going to show you a cute little trick you can do here. So here's the original waveform. And what I'm going to do is I'm going to go through a little process here to show you just what the clicks are. And what I'm going to do is I'm going to clone this waveform. I'm going to make the same exact waveform. So this is the original. All right, so I'm going to come up to functions. We're going to clone this. All right, so I now have this clone. All right. So here's my original. Let's bring back this guy. All right. So this is my cleaned up version. All right. Now I'm going to take my clone and I am going to invert it. I'm going to flip it upside down. And then I'm going to take this pristine version, right, or the cleaned up version, and I'm going to add these two things together. Now, because this waveform is inverted, everywhere these two waveforms are identical, they're going to cancel out, right? So if this had a positive pulse in it, this thing, after it's inverted, would have a negative pulse in it, and those two things would perfectly cancel out. This one still has the clicks. This one doesn't. So those will remain. When we add these two waveforms 50-50, all that remains are the clicks and pops. So we come up to the functions, and we combine the samples. All right, so who do I want? Well, I want to grab number 3 over here. All right, this is what I'm going to import. 50-50%. Right, no lags or anything. We'll just do that. boom, what I've got left is just the clicks and the pops. So let's just listen to this and listen to whether or not you hear any music in here too, or did it just remove the clicks and pops? All right, that's fairly definitive, right? No music in there. That's just clicks and pops, surface noise, and we have effectively removed it from the waveform. Now, if you wanted to make a more realistic sort of degradation of an album, so it sounds like an old 1970s vinyl, you could literally do this kind of thing and then add this back into your pristine waveform. So, using all of these different functions together, don't think of them as individual little things you can do with a waveform, but when you combine them together, you can do some really wild stuff, right? And that's the basic idea. Well, there's plenty more for us to look at, which we will investigate in future videos. Have a good one.